Imagine this, a 35 billion parameter AI model running at 90 tokens per second on a single gaming GPU. A community member tested it on a real coding task, building a PDF merger app with drag and drop, dark GUI, virtual environment isolation, and a Windows installer. The model delivered a working application in 3 attempts. GPT-5, with a vastly larger compute budget, failed all 3. How is this possible? The answer lies in an architectural revolution called mixture of experts, and once you understand it, everything about local AI starts to make sense. To appreciate what MoE solves, you first need to understand the problem it fixes. Every standard transformer model, GPT, Llama, Mistral, uses what engineers call a dense architecture. Every input token passes through every single parameter in every layer, every single time. If a model has 70 billion parameters, processing one token costs proportional to 70 billion in compute. More parameters means better quality, but also proportionally more memory bandwidth consumption, slower generation, and more VRAM required. For local deployment on consumer hardware, this ceiling became painful fast. A 70 billion parameter dense model at 4-bit quantization requires around 40 gigabytes of VRAM, more than any single consumer GPU available today. Even at 8-bit quantization, a 34 billion parameter model barely fits on a dual RTX 3090 setup, and fitting it in memory isn't the same as running it fast. Memory bandwidth determines inference speed, and consumer GPUs have real limits there. The dense architecture hit a wall. Mixture of experts is the architectural path through it. The core insight of MoE is elegant. Not every token needs every neuron. A token representing a Python keyword doesn't need the same neural pathways as a token representing a Chinese character, a mathematical symbol, or a piece of structured JSON. Different content benefits from different processing. Standard transformers ignore this entirely. MoE exploits it. Here's how it works. In a standard transformer, the feed-forward network in each layer is a single network with multiple independent networks called experts. A small, lightweight router, essentially a learned gating network, then decides which experts each token should use. The critical constraint, only k of the n total experts activate per token. If a layer has 8 experts and k equals 2, each token uses 2 experts and ignores 6. The model learns which routing decisions lead to better outputs during training. Over time, experts naturally specialize. Some become better at code, others at mathematical reasoning, others at multilingual tasks. This is the insight that changes everything. MoE separates parameter count from floating point operations per token. In a dense model, parameters equal compute. You cannot have one without the other. In a MoE model, total parameters can be dramatically larger than active parameters per token. The model stores 35 billion parameters, but each token only activates roughly 3 billion worth of compute. Consider what this means for speed. LLM inference on consumer hardware is memory bandwidth bound, not compute bound. The GPU spends most of its time reading model weights from VRAM into compute cores, not doing arithmetic. If only 3 billion parameters are active per token instead of 35 billion, the model reads roughly 12 times fewer bytes per forward pass and generates tokens roughly 12 times faster relative to its total parameter count. This is why 90 tokens per second is possible on a 35 billion parameter model. The mixture of experts approach in large language models has a clean development history. Google's Switch transformer in 2021 proved MoE could work at LLM scale using top-1 routing where each token goes to exactly one expert. Mistral's Mixtral 8x7b in 2023 brought this to the open-source community. 8 experts per layer, each token using 2, giving 46.7 billion total parameters, but only 12.9 billion active. It matched or exceeded Llama 270B on most benchmarks while running on consumer hardware. That was the moment the community woke up to MoE's potential. DeepSeek took it further in 2024 with 2 key innovations. Fine-grained experts, where you use many smaller experts instead of fewer large ones, enabling more precise routing, and shared experts, a small set of experts always active for every token that capture universal knowledge that shouldn't be specialized away. DeepSeek v3 operationalized these at the extraordinary scale of 671 billion total parameters, with only 37 billion active, an 18-to-1 ratio. The current consumer gold standard is Qwen 3.5, 35B A3B from Alibaba, released in 2026. It pushes the design further, 256 total experts per layer, with 8 routed plus 1 shared active per token. 256 experts is unusually large, more fine-grained than anything before it. Each expert uses a very small intermediate dimension of 512, enabling extremely precise routing without activating large network chunks unnecessarily. But Qwen 3.5 has another trick. It combines MoE with a hybrid attention mechanism. Standard transformer attention scales quadratically with context length, making 262,000 token contexts prohibitively expensive. Qwen 3.5 uses gated DeltaNet, a form of linear attention with only linear scaling, for 3 out of every 4 layers. The 4th layer uses full softmax attention to preserve global context sensitivity. The result, native 62,000 token context that doesn't explode memory, extensible to 1 million tokens. The benchmark results confirm the real-world performance. On MMLU Pro, GPQA Diamond and S2E Bench verified, Qwen 3.5 35B A3B matches or exceeds models with far more active compute. On agentic task benchmarks, it actually outperforms the larger Qwen 3.5 122B A-B, suggesting routing efficiency provides a particular advantage in multi-step reasoning tasks. MoE does have real trade-offs. Load balancing is a genuine training challenge. If routing always selects the same experts, others never develop specialized capabilities. Multi-GPU deployments face communication overhead when experts are distributed across hardware. And while active compute is low per token, all parameters still need to reside